Have you ever gazed up at the night sky, a sea of stars stretching out to infinity, and pondered the true nature of our reality? The universe, in all its vastness and complexity, has captivated humanity for millennia. We yearn to comprehend the fundamental laws that govern the cosmos, to unravel the mysteries that lie hidden within the fabric of existence. In our quest for understanding, we have turned to science, philosophy, and even our own imaginations for answers. One of the most captivating and mind-boggling ideas to emerge in recent times is the simulation hypothesis. This theory proposes that our reality, everything we see and experience, might be a sophisticated computer simulation created by a more advanced civilization. It's a concept that stretches the boundaries of our perception and challenges us to question the very foundation of our existence. Is it possible that we are simply lines of code in a cosmic computer program? While it may seem like something straight out of science fiction, the simulation hypothesis has garnered serious attention from physicists, philosophers, and technologists alike. Throughout history, mathematicians and scientists have marveled at the uncanny ability of mathematics to describe the physical world with astonishing precision. Simple, elegant equations can predict the motion of celestial bodies, the behavior of light, and the interactions of fundamental forces. This profound connection between mathematics and reality has led many to believe that mathematics is not merely a human invention, but rather an intrinsic property of the universe itself. One of the earliest and most profound examples of this mathematical underpinning is found in the work of Isaac Newton. His law of universal gravitation, expressed in a single elegant equation, describes the force of attraction between any two objects with mass. This fundamental law governs the motion of planets, stars, and galaxies across the vast expanse of the universe. It's a testament to the power of mathematics to unlock the secrets of the cosmos. Another striking example lies in the realm of electromagnetism. James Clerk Maxwell's equations, a set of 4 elegant equations, unified electricity and magnetism and predicted the existence of electromagnetic waves, including light itself. These equations have had a great impact on our understanding of the universe and have led to countless technological innovations, from radio communication to medical imaging. The discovery of quantum mechanics in the early 20th century further deepened the mystery of the mathematical universe. Quantum mechanics, a revolutionary theory that describes the behavior of matter and energy at the atomic and subatomic levels, is replete with mathematical equations that have proven to be incredibly accurate in their predictions. Our journey into the mathematical heart of the universe begins with a number so captivating it has been dubbed the golden ratio. Represented by the Greek letter phi, approximately 1.618, the golden ratio emerges from the Fibonacci sequence. Each number is the sum of the two preceding ones, 1, 1, 2, 3, 5, 8, 13, and so on. The ratio between consecutive Fibonacci numbers converges towards the golden ratio. The golden ratio's allure extends far beyond abstract mathematics. It manifests in the natural world with a frequency that borders on the uncanny. From seashells and galaxies to flower petals, the golden ratio hints at a hidden order in nature's beauty. Our exploration of the mathematical universe takes us into the captivating world of fractals. Imagine a shape that repeats itself endlessly, revealing infinite detail within a finite space. Fractals exhibit self-similarity where parts resemble the whole. The Mandelbrot set is a famous fractal arising from a simple equation. Zooming in reveals endless self-similar patterns. Nature is an avid fractal artist. Coastlines exhibit fractal properties. So do tree branches and blood vessels, and the jagged peaks of mountain ranges. Fractals show how complexity emerges from simple rules. Our journey through the mathematical universe now leads us to an interesting mystery: the existence of fundamental constants in physics. These constants, such as the speed of light, the gravitational constant, and Planck's constant, are deeply woven into the fabric of reality. If even one of these constants were slightly different, The universe as we know it would be drastically different, perhaps even inhospitable to life. This fine-tuning has led some to propose the anthropic principle, suggesting the universe must be compatible with observers like us. If it were any other way, we wouldn't be here to observe it. Of course, it could be the other way round. We as observers have evolved according to the reality we have been placed in. As we look deeper into the mathematical nature of the universe, we encounter an interesting mystery: the unreasonable effectiveness of mathematics in describing the physical world. Why can abstract symbols and logical relationships predict and explain the cosmos from subatomic particles to galaxies? This alignment between mathematics and reality has puzzled the greatest minds in history. Eugene Wigner called it the unreasonable effectiveness of mathematics, marveling at how equations capture physical phenomena. Maxwell's equations, for example, encapsulate classical electromagnetism elegantly. They describe phenomena from light behavior to electric motors. Mathematics condenses complex principles into powerful statements. Quantum mechanics also uses abstract math to predict atomic and subatomic behavior. Its equations have led to lasers, transistors, medical imaging, and nuclear energy. Why is mathematics such a powerful tool for understanding the universe? Is it a human invention or a fundamental aspect of reality itself? Imagine a civilization so advanced, so technologically proficient, that they possess the ability to create realistic simulations of entire universes. This is the essence of the simulation hypothesis, a mind-bending idea that has captured the imaginations of philosophers, scientists, and science fiction enthusiasts alike. The hypothesis proposes that our reality, everything we see and experience, might be a sophisticated computer simulation running on a powerful supercomputer in some distant, perhaps unimaginable corner of the cosmos. Proponents of the simulation hypothesis point to the exponential growth of computing power, a trend that has held true for decades. If this trend continues, they argue, it's conceivable that future civilizations could develop computers capable of simulating reality with such fidelity that the simulated beings within it would be indistinguishable from real beings, at least from their own perspective. But why would a civilization go to such lengths to create a simulated universe? The motivations could be myriad. Perhaps they are scientists seeking to study the emergence of life and consciousness, or historians recreating the past to better understand their own origins. Or maybe, as some have suggested, it's simply a form of entertainment, a cosmic video game played by beings of unimaginable power. The implications of living in a simulation are profound and unsettling. If our reality is nothing more than a simulation, do we still have a free will? Or our actions are predetermined by the parameters of the simulation? The very nature of our existence could be called into question, our hopes, dreams and aspirations merely the product of computation. The short answer to these questions is, do not worry. If our reality itself is simulated, it does not preclude us from having free will, consciousness and feelings. Yes, free will can be simulated. Evolutionary algorithms is one way of achieving it, but for that, look in our other videos. The simulation hypothesis, while unsettling to some, holds a certain allure for others. It offers a potential explanation for the vastness and complexity of the universe, a universe that seems almost too perfectly suited for life to have arisen by chance. Could it be that the universe's apparent fine-tuning, the precise values of physical constants that allow for stars, planets and life itself, is not the result of random chance, but rather a deliberate design choice by our simulators? If we are indeed living in a simulation, it raises profound questions about the nature of our simulators. Are they benevolent overseers, carefully tending to their creation? Or are they indifferent observers, content to let the simulation run its course? Could we ever hope to communicate with them, to break free from the confines of our digital prison? The philosophical implications of a simulated existence are far-reaching. If our thoughts, emotions and experiences are all products of a computer program, what does it mean to be human? Do concepts like love, purpose and morality hold any real meaning in a simulated world? These questions challenge our fundamental understanding of ourselves and our place in the cosmos. The simulation hypothesis also forces us to confront the limits of our own perception. If our reality is a carefully constructed illusion, how can we be sure of anything? What if the laws of physics, the very foundation of our understanding of the universe, are simply rules programmed into the simulation, subject to change at the whim of our creators? While the simulation hypothesis is a captivating thought experiment, it remains firmly in the realm of speculation. To date, there is no definitive evidence to prove or disprove the notion that we are living in a simulation. However, some scientists and philosophers believe that there might be subtle clues, telltale signs that could betray the artificial nature of our reality. One line of inquiry focuses on the search for glitches in the simulation, anomalies that defy the laws of physics or suggest a break in the continuity of reality. These glitches could take many forms, from objects appearing or disappearing unexpectedly to sudden shifts in the fabric of space-time. While such anomalies are often attributed to errors in observation or limitations in our understanding of the universe, some proponents of the simulation hypothesis believe they could be evidence of a malfunctioning program. Another avenue of exploration involves searching for the fundamental limits of simulation. Just as our current computer simulations are constrained by processing power and resolution, a hypothetical universe simulation would likely have its own limitations. Identifying these limitations, such as a maximum energy level or a minimum unit of space, could provide evidence of an artificial reality. Have you heard about speed of light being the ultimate speed limit in our universe, or the Planck length being the minimum distance? The quest to determine whether we are living in a simulation is ultimately a quest to understand the true nature of reality itself. It is a journey that takes us to the very edge of human knowledge and forces us to confront the mysteries that lie at the heart of existence. The simulation hypothesis suggests our universe might be governed by elegant mathematical principles, much like efficient code in a sophisticated program. This efficiency could hint at intelligent design, reflecting the computational prowess of its creators. Could our continuous reality be composed of discrete units akin to pixels on a screen? Quantum mechanics hints at a granular universe, aligning intriguingly with the idea of a simulated reality. Max Tegmark's mathematical universe. Hypothesis proposes that our universe is a mathematical structure, not just described by mathematics, but fundamentally equivalent to it. This idea converges with the simulation hypothesis, suggesting our reality might be an ultimate form of simulation. While the simulation hypothesis is captivating, we must avoid overusing analogies between digital simulations and reality. Mathematical laws describe observed regularities, but do not necessarily dictate the universe's behavior like a computer program's code. The anthropic principle offers an alternative to the fine-tuning argument, suggesting we find ourselves in a life-permitting universe by chance. This principle highlights the importance of considering selection effects when evaluating seemingly improbable events. The simulation hypothesis blurs the line between the real and the virtual, challenging our understanding of consciousness and reality. If our reality is simulated, our perception of the world might be fundamentally limited, much like a character in a video game. Even if our reality is a simulation, it is filled with awe-inspiring wonders and meaningful experiences. The simulation hypothesis challenges us to find purpose and live with intention, regardless of the ultimate nature of our reality.